we're now going to consider a slightly more rigorous approach to the solution for the electromagnetic potentials in the general case. So we're going to concentrate again on the electromagnetic potential. I'm just going to rewrite that. Del squared V minus 1 over c squared d2v by dt squared is equal to minus rho over epsilon naught, where v is a function of r and t, and rho is also a function of r and t. We'll be able to use the same arguments for the vector potential. With a vector potential, you can separate it and do it Cartesian component by Cartesian component, so it's the exact same argument. I'm going to label this as equation 1. Now, the approach we're taking is a very standard one. Essentially, we've used this several times before, where we consider the force on a point charge, and then we replace the point charge with the charge density rho over a small volume dv, and then we integrate over a volume in order to calculate the total force. In the same way, here we're going to solve for a point charge at the origin, replace it with rho dv, and integrate over all space. So let's start by writing that down. So we're going to assume a completely mythical object, q of t, it's a time-varying point charge, and we're going to place it at the origin because that's the most convenient. And then what we're going to do is we're going to replace excuse me, q of t with rho of r and t dv and integrate. That's what we're going to be doing at the end. If you've studied Green's functions, you will notice that this is effectively a Green's function argument, but without the full mathematical formalism. Now, let's just note first of all that if we have a point charge at the origin, away from the origin, we have a much simpler equation to solve. We need to simply solve del squared v minus 1 over c squared d2v by dt squared is equal to 0. And that's true at every other point in space. If we just consider, if we integrate equation 1 in a little volume delta v near the origin, then what we're going to find is the following. We're going to find that we've got the integral around delta v of del squared v minus 1 over c squared d2v by dt squared, that's the integrand, dv is going to equal, and now we need to have the integral of rho, which is minus q of t divided by epsilon naught. So that's something that we just need to keep in mind. That's equation 2, and we're going to have to satisfy that at some point. Now what we're going to do is we're going to develop a solution for v, and we start by noticing that v must only depend on the radial coordinate. That just comes from the symmetry of the situation of r only. If you've got a single point charge at the origin, then there is nothing giving you any other form of dependence. So v is equal to v of r, where r is the magnitude of the position vector, it's the radial component. So if we now replace the del squared with the appropriate spherical polar form, we find the following. We get a 1 over r squared d by dr of r squared dv by dr minus 1 over c squared d2v by dt squared is equal to 0. This is getting a little bit simpler. There's an absolutely standard substitution at this point. It's often used in atomic calculations, and it's to do the following, is we write v of r and t in terms of another function. In this case, I'm going to call it chi of r and t divided by r. And when you substitute that into this little Schrödinger equation, equation 3 up here, it's not actually the Schrödinger equation, it's the wave equation, sorry, I misspoke. Then what we find is d2 chi by dr squared minus 1 over c squared d2 chi by dt squared is equal to 0. And this is just simply a 1D wave equation. It's very easy to show that the 1D wave equation is solved by writing chi of r and t is the sum of some function f of r minus ct plus another function g of r plus ct. Those are essentially arbitrary functions. They will solve that so long as they have the appropriate differentials. One of them represents an outwardly expanding wave. That's the, let's make this in a different colour to make it stand out. So the expanding wave is, let's say, is f, because that's the r minus ct, and we have a contracting wave, which is the g of r plus ct. And we're only going to want to pay attention to the expanding wave. That's the solution that we want. So that tells us that we can write v of r comma t is this arbitrary 1D function, f of r minus ct divided by r. And I just want to notice that r minus ct divided by minus c is equal to t minus r over c. So those are just a rescaling, and we're going to use t minus r over c in a second. So how do we choose this function f? Well, we're going to choose the function f to satisfy equation 2. Now let's just go back up a second to look at equation 2. Here's equation 2. It's this equation here, this wave equation, where we've got a source term on the right. And for instantaneous time, we know that we can solve that by writing the following. We can have v of r comma t. We'll solve that if we have the solution q of t minus r over c divided by 4 pi epsilon naught r. And that, of course, specifies the form of f as well. So that solution satisfies all conditions that we require. Using this solution, we're now going to integrate, and remember that we replace the q with rho dv, and so the final solution for the potential v of r comma t is equal to 1 over 4 pi epsilon naught volume integral rho of r prime comma t prime divided by the magnitude of r minus r prime dr prime, where we've defined t prime is equal to t minus r prime magnitude divided by c. The same argument can be used for the vector potential A. And what I want to note here is that we've introduced the idea of retarded time, t prime, which is t minus r prime over c, without actually any kind of heuristic argument, without any approximation that we used in the first video. In the first video, we sort of waved our hands a little bit and said, well, it takes time for electromagnetic waves to propagate, therefore we'll use these sources at an earlier time. Here we found that solution actually naturally comes out of this 1D wave equation, which of course itself is a way of saying that it takes time for electromagnetic information to propagate, but this is now a formal definition. So what we've done is we've used an approach that allows us to create a solution for the potential, and that solution matches the solution we claimed in the previous video. In the final video, if I have time to record it, I will go through a Green's function derivation. This is mathematically much more rigorous. It's potentially much more challenging. If you're not comfortable with that kind of thing, then feel free to ignore the video. If you're interested in formal approaches, then you might want to watch it.